No,
What's easier? Well, if you use kilograms, you don't have to convert it.
Okay, what's more likely to be on the test?
Grams.
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 Okay, let's do 200 grams and 100 grams. Did you start it again?
Yeah.
Okay, this is part 2. Attention. Can we, just for the ease of things, can we say that G, instead of 9.8, G is equal to 10? You good with that?
Yeah.
We'll just round up at 9.8 to 10, and that's easy to figure out. Okay, draw this on your page, and then label the forces of gravity on each mass. Can we call this FG1 and this FG2? Are these two forces of gravity the same?
No.
When you look at these forces, it's important to think about the direction. They're both pulling down, right? But are they pulling together or against? They're pulling against each other, right? But they're both being pulled down. And that's what a pulley does. A pulley takes two forces that are both pulling down, and it makes them fight against each other. Okay. Put your hands like this. Your elbows are the two masses, like that. Okay. Now flatten it out. The two forces are the same, but now one's pulling to the left, and the other's pulling to the right. It's like a tug of war. So you can draw it like this, and you can say, here's my 200 grams and my 100 grams. And you have your forces of gravity. But now your forces of gravity, strangely, are pulling right and left. We know that they're not really pulling right and left in reality, but it's kind of a nice way to think about it, because it takes away that they're both being pulled down. They're just pulling against each other. So it's like a tug of war. Bless you. Okay, let's work out the forces on this. 200 grams is how many kilograms?
0.2 kilograms.
0.2 kilograms, and this will be 0.1 kilograms. Bless you. Okay, so what's the force of gravity on that one? Yeah, it's 2, right? 0.2 times 10 is 2. So this is going to be 2 newtons. And what about the other side? Wow, this is really simple. I should have kept it kilograms. Luca. Good question, actually. Great question. To find the force of gravity, we use that formula right there. And we say Fg is m times g. So for the 200 or 200 grams, it's 0.2 kilograms times 10 is 2 newtons, right? So we use this. But Luca's right to ask that question because they're not accelerating at 10, right? So why are we using g for this if it's not accelerating at 10? Luca.
Second part, sort of like combining the force that two objects have on each other with gravity and stuff like that.
Yeah, that's absolutely right. Let's give him a golf clap.
Wait, what?
So what he said was, we're taking the force of gravity and combining it with another force that's acting on the object. So if there was no tension here, it would accelerate at 9.8, right? And so we know that force down is still mass times 9.8. There's just another force up. And now our job is to find that. Okay. What is net force?
Total force.
Okay. Total force. Anything else?
All the combined forces.
Oh, say that again.
All the combined forces.
All the combined forces. So this is something, if you're like, okay, give me something to remember, Mr. E, like what can I use? What do I remember on my test? There's two things you remember. Net force is always the sum of all the forces acting on the object. That's number one. You can always count on this. The net force is always the sum of all the forces. And it's also something else. What's the other thing? You can see it in the room right now. Oh, he did it again. F net is MA, always. Thank you, Daniel. These two things you can always count on. Always remember those two.
So in this scenario, F equals FG. The acceleration is gravity.
It's not going to equal FG, but it's FG is involved for sure. It'll be the sum of the FGs for sure. And now is when you have to kind of decide whether you are a mathy person or whether you are a real worldy type thinker. Turn to the person beside you and decide whether you're mathy or whether you're a real worldy. What did she say? She's what? See, I know I can see her eyes going. It's okay, you're not on video. If I do it, I'll be on the video. Put your hand up if you're a real worldy thinker. Okay, put your hand up if you're a mathy thinker. Interesting. You put your hand up twice, Daniel. Well, eventually we're all going to do both. That's for sure. Yeah, go ahead. If you're mathy, there's an extra step you have to do. If you're real worldy, this is all you need.
If you're what?
If you're mathy, what do you need to label always? Nathan. Good, very good. If you're mathy, you're going to say, this is positive. Probably that's going to be positive just because it's bigger. And you will label this side as negative. And so instead of this being 1, that's now negative 1. This is going to be a pretty simple example, but so first, we find the net force on the system.
This is, wait, you're teaching us how to do this.
Yeah, I'm teaching you how to do this right now. So the F net on the system equals the sum of all the forces, so it's Fg1 plus Fg2. Now, if you're real worldy, you don't have to do this. You already know the net force. Who already knows what the net force is? Oh, Kiana does. Kiana, what is it?
It's 1.
It's 1, right? Because she's saying, well, there's 2's going this way, and it's pulling back with 1, so this one wins by 1. If you're mathy, you're gonna be like, no. You cannot do that. You have to say -1 Newton plus +2
Which one is the
Newton.
right answer?
Well, they're both the same answer.
Oh shoot.
Yeah, you're bad.
So the net force on the system is 1
That was
Newton.
no fun. How was that fun? I was seeing his music.
Okay. So if I take this, right now it's 2 newtons and 2 newtons, right? But if I take this off, now I have 2 newtons and 1 newton, and that's why this is gonna accelerate up. And it'll have a net force of 1 newton. Okay, what can we find with this now? We know the net force. What can we use it to find? Luca?
Sorry, this is probably just me not paying attention.
No, that's okay, go ahead.
Temperature of object go down.
Yes.
Okay, so, yeah.
This one's gonna go down and that one's gonna go up, right? But in our example, if we straighten it out, it's gonna go that way. And this one's pulling back the other way.
So you just decided down was also different times.
Well, no, actually, in this case, because there's a pulley, down is positive over here and down is negative over there. It's confusing. But that's why we flatten it out.
Wait, I need to.
And we say, well, we're not really working with down anymore. We're actually working with a force pulling right.
So right is
force
down and
pulling
left is up.
Yeah. Yeah, but that's only if you're math.
No, right is down and left is down. But
So then
right is
why aren't they
positive,
just both negative
left
or
is
both
positive.
positive?
Look at your two masses, right?
Yeah, that one's heavy.
Now if I take this one off, this one's heavier, it's gonna pull, right?
Yeah.
That one's pulling down as well.
How is that
But because it's on the pulley, it's pulling against this force.
So it's just pulling down less.
Yeah.
Exactly.
Would it be fair to say that you're, like, it's less about, like, down and up and more about, which one is heavier, because that will affect the net force.
I'm with Luca.
Exactly.
Okay.
Exactly. So if it works to flatten it out for you, and you say, I'm gonna forget about up and down, I'm gonna say it's a strong force to the right and a weaker force to the left, then do that. If it works for you to think, no, they're both pulling down, but because of the pulley, one's pulling against the other, then do that. But this way has to be negative and the heavier way has to be positive. Because positive and negative pull against each other. Does that make sense? I'm sorry.
What is the FNet system? What is that 1 newton tell?
This tells you the net force on the whole thing.
1 newton.
Yeah, 1 newton. And so that's going to allow us to find something very, very important.
And if it be
Armand.
Acceleration.
Very good, excellent.
Inertia?
Golf clap for you.
inertia, what is it?
He said acceleration. So our net force, our F net of the system, is equal to ma, right? So how do we solve that for acceleration? Well, eventually we will. But right now, this is equal to the mass of the system times the acceleration of the system. So how do I solve that for A, Nathan?
System over mass.
Good. I'm going to do the F net of the system over the mass, but it's got to be the mass of the whole system. Okay, figure that out. See what you get. don't know what that is. 3.3, yeah.
One force is solid, just to make it easier. You just make the bigger numbers.
Would the mass of the system be 300?
Yeah,
Okay.
300 grams, so 0.3 kilograms, right?
How do you get your arrows like that? That's what
I like the arrows.
What's the acceleration and what are we?
So this is a simple example, but I'm taking you through it because it gets a lot more complicated, and I want you to understand the underlying concepts. Let me ask you a question. We found out that the net force on the system was 1 Newton. Is that the same as the net force on this mass?
No.
No. Is it the same as the net force on the other mass? No. The acceleration of the system is 3.3 meters per second squared. Is that the same as the acceleration on one mass?
Yeah, would it
Yeah.
it would be, yes.
Yeah.
Yes.
If you release this and the whole thing accelerates,
It also accelerates at 3.3.
Yeah.
this will accelerate at that rate and that
Yes.
will accelerate at that rate. They have to, because they're tied together.
Otherwise you'd be like floating, it goes faster.
That's right, Luca.
So this sort of setup just kind of like equalizes the acceleration. One goes up and one goes down, but it is equalized.
Exactly.
So one is positive?
Yeah, so I would imagine this as being positive. It's accelerating in the positive direction at 3.3. This one is accelerating also in the positive direction at 3.3. Even though they're moving in opposite directions, the whole system is kind of moving the same.
Wait, how are they both positive? How is one not negative?
Because this is positive and this is negative.
One's going up, one's going down.
Yeah, so wouldn't the left one be negative?
It's not like the previous equation.
No,
It's like
because
it's similar to their own
If
thing.
you flatten it, the whole thing is moving that way, right? Positive.
Oh yeah.
Because this mass is moving towards a positive, this mass is also moving towards a positive. Even though in reality, one's moving down and one's moving up, they're kind of moving in the same direction. That's what a pulley does. That's what simple machines do for us. It changes the direction of a force.
Are we gonna
Makes
look at
sense.
simple
So
machines
one's
then?
negative, one's positive.
They're both positive accelerations.
Oh,
It's less in like up and down, negative and positive, and more left and right.
Correct. That's right.
both positive
Um,
accelerations, but negative.
This right here is the key to all these tension problems. Can they see me on the video here?
Yeah.
Okay. This is key because this acceleration is the same for each individual mass as it is for the system. So you always want to find the acceleration because that will give you the key to the whole thing. How many minutes am I at?
Oh, 18.
Okay, stop it. That's part 2.